Okay, so since this is a new chapter, we've got a bunch of definitions to start off with, and to begin with, oops, I'd rather have that be a different color. Angular position, angular velocity, and angular acceleration. All right, so we're now dealing with the rotation of bodies around a particular point. So we are very concerned about where the center of rotation ends up being. And for the moment, I'm going to take the center of rotation to be the origin of a coordinate system. So let's say we have some object. And if we look at it, it is some distance away from the center of the system and at some angle at a particular moment. Now as time moves on, maybe the object moves to a different position. Same distance away, but now a different angle, so we'd have a theta initial and theta final. But either way, the angular position. Now for an angular position, we do need to think about where the 0 point is, and traditionally 0 degrees would be measured along the positive x-axis. Okay, well that's great. As you measure the angles, angles are positive as you go around in a counterclockwise manner. Now again, that's tradition. Of course, just with everything else, like usually we take downward as positive when we've got free fall. Sometimes you can take downward to be positive. Sometimes we switch the direction that we think of as positive here as well. But the traditional way of thinking about it is that counterclockwise is positive. If we had an object that has instead gone around, whoopsies, has gone around the other way, then angles here are negative. Okay, and to finally wrap it up, the symbol that we're using for angular position is just theta. It's a little bit like when we had x out of x, y, and z directions. There are other angles of rotation you could think about. For instance, this particular one, theta, is an angle for going around the z-axis. You could have an angle for going around the x-axis or an angle for going around the y-axis. But we're just focused on rotations in the xy plane at the moment, which would be rotations around the z-axis. All right. Let's carry on to the next step. I've got these two different angles, and if you took the final angle divided by the initial angle and divided by the time elapsed to get there, that gives you omega, the angular acceleration, or sorry, angular velocity. There's another way of thinking about it. Each one of these positions, we could figure out where they are, and we could think about the arc that's followed. So here, the arc would be r delta theta, or r times theta. So we could think about kind of what would happen if we took a derivative. This is more for the next section, actually. But anyway, we're changing an angle by theta. If we take and make that very, very small, if we take the derivative of theta with respect to t, that gives us our instantaneous angular velocity. And of course, we can extend the idea one more time and have, what if we change omega? If we take omega final minus omega initial and we divide by an elapsed time, that gives us alpha, and that is angular acceleration. Okay, of course, we can also do that as a derivative. The derivative of the angular velocity with respect to time gives us the instantaneous angular acceleration. Okay. That's pretty much it. We're just looking at definitions for the moment. We're going to start doing rotational kinematics up next, so look for that. There are two different versions, one where we use these calculus definitions and another one where we presume that the angular acceleration is constant, which leads to a series of formulas just like we had for linear kinematics. So look forward to that in the next videos.